Let's take a look at some examples for confidence intervals for means. The first example, the sportscasters at a small news station wish to estimate the number of hours that men spend watching sports events each week. They surveyed 50 men locally and found that the mean was 4.0 hours per week. From previous studies, they found that the population has a normal distribution with a standard deviation of 1.1 hours. Find the margin of error and the 95% confidence interval for the mean. When reading this problem, we get some information. We know that our sample is 50, N is 50. They surveyed 50 men. They found the mean was 4.0 hours per week. So I'm going to highlight that word mean as well. That is our sample mean, 4.0 hours per week. From previous studies, they found the population has a normal distribution with a standard deviation of 1.1 hours. So this is telling us that the population standard deviation is 1.1 hours. That word population is what clues us in that we are working with a population standard deviation. And this should be hours per week. It should have the same units as our mean. So small typo there, that's a good correction. Find the margin of error and the 95% confidence interval for the mean. So 95% confidence level, 0.95. This alpha being 0.05 is just another way to write our confidence level. Alpha is 1 minus the confidence level. The margin of error part, that's our error bounds for means. That's the middle calculation that we have to make that we then add and subtract from the sample mean to get the confidence interval. So we'll be pulling that out of the template as well. Let's take a look at the template. All right, so let's enter that information into our table. We don't know the population size, so we're going to leave that blank. We almost never know the population size. We usually only know the sample size. Now in this template, I have some data on the side. I'm going to take that data out. I only have statistics given, not the raw data. So I need to take that out and then put in the statistics that I have here. So it's asking me for the sample mean, the sample size, and the sample standard deviation. But notice that if a number is here, the template toggles to tell you, since you've provided data, I'll compute the values of the statistics, the sample statistics. And it says the 3 cells will be ignored, and we don't want that. So make sure all the data is out so that we can then put in our calculations. We do know our population standard deviation. That was given to be 1.1. So we're going to put that in there. Sample mean was 4.0. Sample size was 50. Sample standard deviation is not known, but that's where this template can be used for both types, whether we know the population standard deviation or we don't. And what makes this really interesting is that the template, if you watch the formulas on the side, you can see which formula is being calculated. So if I take this population standard deviation out, notice right here, this formula changed from a normal inverse function to a t inverse function. So I'm going to put this back in. We'll do an example with t momentarily. And here we have our confidence interval, 3.7 to 4.3, and I'll write that on the page. And we also have our margin of error right here, this 0.30. This is what they are asking for when they ask to find the margin of error. We're looking for this calculation for the margin of error right here. Okay, so let's capture that. I'll do a quick screenshot here. And as you're working through these templates, you can make copies of the sheet that you're on. Just copy that template over into new sheets to do additional problems, for example. I'm going to post my screenshot right here. And there we can see our lower confidence limit, our upper confidence limit, and then the margin of error there. So our margin of error, or error bound for the margin, different books use different lingo, and that's okay, was 0.30. And then for our confidence interval, 95% confidence interval, which we have here, 95% confidence interval, that's the 3.7 less than mu less than 4.3. So we are 95% confident that the true population mean of the number of hours that men spend watching sporting events per week is between 3.7 and 4.3 hours. And we could write that out in a statement. Let's take a look at the second problem. Freshman GPAs. First semester GPAs for a random selection of freshmen at a large university are shown. Estimate the true mean GPA of the freshman class with 99% confidence. Assume that this population standard deviation is 0.62. So we'll use that normal distribution in the template. Remember, the template automatically chooses it based on what we're putting in. That's why it's really important to be precise on what you're putting in the template. This one has data. Now, I will comment at this point that the format in which this is set up isn't very friendly for using Excel and Google. So we would have to type all of this out, and there's a chance for mistakes. So as you're going through, check off each number as you type them in, or make some kind of indication. And then as we do this, you'll be able to go back and check. If you start getting frustrated in the homework, with the homework, you can do a copy paste into a spreadsheet. That seems to work pretty well. So try that instead of typing it in. But if you have a problem where you have to type it in, try to be really careful in entering the numbers. So I'll pull up the template here. I already have the data entered on the side. You can see it goes down pretty far, down to cell 37, and I started in cell 2, so I have my 36 values. And then I'm going to put in my assumed population standard deviation, 0.62. So I will change that. This information was left over from the last problem, so I'll delete that out. And then it's asking me for a 99% confidence interval, so I'm going to make that change here. And some things to look at. So I have not hit entered yet, so it's not calculating the correct critical value yet. But I have my sample size. Notice it's doing a norm inverse function because there's a population standard deviation there. And if I hit enter for my 99% confidence interval, the critical value changes to 2.58. And then my margin of error is 0.27. Lower confidence limit 2.55. Upper confidence limit 3.09. Since we're given the raw data here with 1 decimal place, we want our confidence interval to have 1 more decimal place. And this is coming from the rounding rule for sample statistics or population proportions. When we calculate a mean or a standard deviation, we want that calculation to have 1 more decimal place than our given data. Given data has 1 decimal place, so our calculation should have 2 in the final result. All right, and I know this is pretty small on your screen, so I'll write it down and then we'll make it a little bigger. So we're looking for the 99% confidence interval. We would have 2.55 less than our mean, less than 3.085, which would round up to 3.09. And this is talking about GPAs. If you were to look on your own transcript for our college, you would see your GPA with 2 decimal places. Different colleges round their GPAs differently. Some colleges round to 1 decimal place, some to 2, some to 3, and I've seen some that even round to 4. So it really depends on the standard of the college. But this particular college that we took from, it only rounds it to 1 decimal place. Then we would write this, interpreting it by saying we are 99% confident the true mean of freshman GPAs is between 2.55 and 3.09. Now, one question for you before we wrap up this part of the lesson. If I go for a 95% confidence interval, how does that change the interval? Does the interval get bigger or smaller when we decrease the confidence level? If we make the confidence level bigger, that means we want a bigger interval. So we're capturing a bigger interval to try to grab that mean, or to grab that population parameter that we're estimating. So just to see this in effect, notice the confidence limits down here. Remember 2.55, 3.09. If I change this to a 95% confidence interval, notice they shrink. The 2.55, the lower limit, is now 2.62, so it's gone higher, closer to that mu in the middle. And then the 3.09 that we had before is now 3.02, so it's going down. So the lower limit goes higher, the upper limit goes lower, so they're making a smaller interval. It's definitely something to be aware of in how the confidence level changes our interval. That's important. We'll wrap up this lesson with the minimum sample size needed. So we have a formula here for the minimum sample size. Really, we're taking that margin of error, the error bound for means, and solving that formula for n. So if we scroll back up very quickly, we take this formula right here, the margin of error, work some algebra on it, and we get n equals, and then everything else on the other side. And so that's how we find this minimum sample size formula. There's a desired confidence level. That confidence level will give us our z alpha over 2, our critical z-score. We know the population standard deviation, or we have an estimate of it, and then we have some desired margin of error that we're striving for. And then if we use this formula here, solved for n, this tells us the minimum sample size that we would need to achieve the confidence interval with that particular confidence level and that particular margin of error. In these cases, just like before with the proportions, we would round the answer up to a whole number. No matter what that decimal is, we are always going to round up. So if the decimal is 0.001, we're going to round to that next whole number. So let's see how that would work in practice with a problem. Here we have a scientist wishes to estimate the average depth of a river. He wants to be 99% confident the estimate is accurate within 2 feet. From a previous study, the standard deviation measured was 4.38 feet. How large should the sample be? Notice the question. We're not being asked what's the confidence interval. We're being asked how large is the sample. So let's gather some information that we know. We have a 99% confidence level. So confidence level is 0.99, which means alpha is 0.01. Throwing this alpha out here just so that you know where it comes from. It's coming from the extreme outsides of the normal distribution graph, the tail part, and it's what gives us our critical z value. Accurate within 2 feet. Let's hang on to that one for a second. We'll come back to it. In a previous study, the standard deviation was 4.38 feet. So standard deviation, 4.38 feet. We don't know n. The only thing that's missing from this is our margin of error. And that margin of error is the 2 feet that we want the estimate to be within. That's the margin of error. That's exactly what that means. So here are our values. Let's go to the template and plug them in. And we're going to use the lower part of the template this time instead of the upper part. And this one has nothing to do with the data on the side, so we don't have to worry about that. We know our population standard deviation, 4.38 feet. We know our error bound for the mean, or our margin of error, that's 2. And we're being asked for a 99% confidence level. In a 95% confidence interval, we don't need as big a sample as we do for a 99% confidence interval. We need a bigger sample for a larger confidence. And so we get 31.8. And a reminder, always round up. So we would round this to 32. So we'll take this snapshot, plop it over. A reminder to always round up, so we're rounding up to 32. The sample should be 32 or larger. So we're talking about depths of a river. He's going to have to make 32 measurements or more to have his 99% confidence with accuracy of 2 feet. I would like you to try number 4 on your own. See if you can get the answer and check your work.